30 minutes for your input, and we have about 20 minutes for input and 10 minutes for questions and answers. Good afternoon, dear colleagues. I'd like to present my report today on bio-inspired analysis of technical contradictions in trees. The project was managed by several authors from Russia, from ITMO University, and from Beijing University of Technology, PRC. There are two authors from ITMO, and Xin Min is an author from Beijing. Xin studies in our university. She's my student. She got very good results, and so she is part of our today's report and work and input. Now, our objective, the objective of our presentation is discussing the connection between biological and technical aspects of passing on here data information when attempting to solve an inventive problem. So this will be a status update on the project, and the second objective is to consider the problems of genetic LT coding of properties in TCs, where LT are length and time dimensions. These are two objectives. First one is a bigger one, the second one is a smaller one. Now let's proceed. In this slide, you see the main directions in trees. This is the directions in the field of this biomimetics science, which works with natural systems, building models, technical systems, and technologies. So this is a way to transfer biological effects to technologies, to the technological domain. Historically, biomimetics has overlapped with trees when biological effects became part of the trees toolkit. They were included in the trees toolkit in line with chemical, geometrical, and mathematical parameters. There are some similar analogies and equivalence in between that. It used to be called bionics, but currently they don't use bionics in the English language very often, so that's why we are currently trying to call it biomimetics like they do in the West. In accordance with the reference materials, we can tell you that biomimetics is going down the path of using these three lines. So the first line is developing those biological effect indices by means of data compilation, and it works with the software for semantic test processing. So this is an area which we started to develop. So we started developing that as typical approaches, and this is what currently being developed in such a way. So we see that these indices are being developed. We are searching for these indices. We do not do that, so I'm not going to dwell into this subject specifically in greater detail. The second area is those ways to use typical approaches to resolving biological contradictions. This is the same what we had with the famous Altshuler matrix 39 by 39 and those typical methods to address biological contradictions. A few words about it. So we saw the development of this biotrees contradiction matrix. We are not doing that either. So the second area which we are focusing is called the genetic modeling in technical systems design. Biomimetics is not just solving inventive problems, but it also addresses design of technical systems. So again, we see some overlappings in different areas, genetic modeling and productive areas as well as genetic algorithm. So we see that there is this structural synthesis and passing on hereditary information and design quality evaluation. So we will focus on this specifically. I will speak about it right away. So we are also doing structural synthesis, but specifically I'm going to focus on two other areas. So this is the bio-trees contradiction matrix. It was developed by a group of researchers led by Nikolai Bogatyrev and others. He started their activities, his activities in the Soviet Union, as far as I know. They are working in the UK, and they developed this bio-trees contradiction matrix on the edge of psychology, biology, and other sciences. We don't want to describe all these parameters, but we see that this matrix was developed in 2019. This was their development. So the key difference, so the principles are the same. We see that there are some improvements and some deterioration. So again, there is the split in those columns and lines. So the matrix is very extensive, and the developers split it into sections. So we have different sections in this table. There is space, time, field, energy, structure, information, and regulation. So again, substance, and the same here, substance, space, and others. So this has been split into sections. There are also some empty cells, something like that. Those green ones are empty cells. They are for filling that and extending that further. These are these diagonal overlapping. So in this, there are those numbers of methods used, applied. We can add psychology, biology is also part of that. So apart from the technologies and besides technology. So again, this is something which is very extensive, reaching to 20,000 of items. Now, the key problem or issue about it so the key issue about transferring this information is about having this capacity and looking at this third area, what is considered a gene in a technical system. And I would like to demonstrate it to all of you today. Now, this is the notion of a gene as it relates to a technical system. I believe that this is the key issue. What is a gene when it comes to a technical system? We know that a gene is a unit of sending biological information in biological systems. So what do we consider a gene? Speaking of a technology, when we try to use our bio approaches and work in this technology. This Article 6 by Mr. Shai suggests that models of simple physical objects such as a mass, spring, shock absorber, resistor, coil, capacitor, beam, and actuator are models of complex objects such as mechanical or electrical amplifiers can all be genes or unidirectional geodrives or electronic rectifiers. So all these can be genes. So this is an example of an electric rectifier to the left here. So this is the diagram, the scheme of such a spare part, and then there is this gene as a graph, as a diagram of this elementary unit for sending this information in that. So there is this graph which corresponds to the source. So we see this capacitor, diodes, load, and all that. And we see that the current is unidirectional, flowing in this direction. So there is this alternating current between these plus and minus, and this plus and minus right here. So we have it, this rectification. Mechanical equivalent, train wave gearing. So this is what you see here to the right. So in terms of, and when it comes to the authors of the article, so this is a mechanical similarity of a rectifier. So this is just one gene which will represent it within a technical system. Then there is this bridge circuit rectifier. A gene has graphical chart of potentials. So we see one load of capacitors and 4 diodes, and then there is a graph schedule, and then there is this mechanical equivalent with all that, having all those springs and rods. We see that this is the rod C and D, which is always in the mode of springing, despite of this impact from A to the top or to the bottom, C and D are always squeezing thanks to these springs and rods. So this is the mechanical equivalent of this bridge diagram. Now, bridge circuit rectifier. So what is it about sending this hereditary information? Hereditary information. Well, there is nothing like that there. So this is just to demonstrate that it was an achievement in that there was a new concept developed, a concept of having this amplifier of rotation. They took an electrical analog equivalent and they created an amplifier of this rotating momentum as a mechanic output. So this is there is no way there is this transfer, in my opinion. The next example, so let us just try to focus on this next example, which is genetic algorithms. So you can see there in the picture there is this genetic algorithm. This algorithm and these algorithms in this problem I'm going to describe. They all come from an article authored by some other researchers. I will give you the name later. So you see that we have this modeling of an image. So there is this genetic algorithm which is used to transfer this hereditary information in image processing. So this is what we have as a legacy from another image and transferring that to a new image, driving a new image based on the previous ones. So there is a new generation of this solution. Genetic algorithms. So what is it about? Now, what are genes in this diagram? So these are more specific examples. So we have a gene of a font size. So we have this font, for example, from 2 to 50, and then there is this one gene. The second gene is the type of the font. It can be Arial or Times New Roman or some other fonts. So this is the second gene. Then there is the background color. So we have this letter itself, and it has a color, and then also there is a shape and the background on which the letter stands. And then there is this type word. Alexander Borisovich, you have 15 minutes. Fine. The technology of getting a new image is having this expert. When an expert selects an existing image, and then based on that, this expert looks into the typical method matrix they took from Altshuler, they derive something new. So they they generate a result based on all that. So let's look at this example. For example, this new type shape of a ladder, which is extended, or there is this principle squeezing or crushing. So this is what they get out of that. So these are the solutions.
So what we suggest as the example of genes of transfer information, so we suggest physical technical systems, and also we use the system of kinematic quantities and values. So physical technical systems, the idea of length and time genes as a method of coding for passing on hereditary information was first proposed in 2008. So 15 years passed, and I was the author of that project. And right now I'm giving you a report what was done within this thing. What was actually achieved in this method, LT system. So gene of length and time. So if we look at the kinematic values, we can see the dimension in meters and seconds. So we have 5 main values, and also Bartini's meters and seconds, but all of them are like by dimensions. So here, for example, length, here is L is time. So how we can get time gene? So the length is being divided by the period, and then we get the result. So for English speakers, English speakers, you can see it later a bit. So what was achieved in the system of technical direction? So inventive tests and also design tests. I won't talk a lot about design tests, I don't have enough time, but as per inventive tests, we will go on math model of passing on hereditary information from prototype to a new solution, and prototype decay and parental trend. So what was achieved here, and who still works there? Besides us, here Professor Reich works pretty successfully from Serbia, from Belgrade. So he achieved something here. And what was actually offered here, proposed? We make a matrix of usual approaches, like in matrix of Altshuler, and also Professor Reich, what he did. So in Altshuler, weight of moving object, stationary object, and also length of moving object and stationary object. And if we take the weight of stationary object, so there is a value in the matrix of Altshuler, but what Reich proposes to multiply it like length and speed, how the hereditary stuff has been passed on. So here you can see here on this chart. So one property should be proved, another property is decreased, so as the model as the outcome is baby, and so this is the usual output. A very simple model, how from B system to alternative properties of technical contradiction, we have one example. So this is the main scheme. So you have 10 minutes to go together with questions. Passing on genetic information in the LT dimension method. So here we can see what is worsening and what is improving. So here is the weight of the unmoving object, stationary object, and here is the dimensions, and here the result of Altshuler table, and Professor Reich is suggesting to call it anti-weight and equipotentiality. I guess it's a bit kind of too much thing, but still, this is problems in methodology. You see, Altshuler has got in his temple where the dimensions are not being determined. But for example, the repair adaptivity and etc. Flexibility, it's not really determined. So we decided to use the given two objects, and we decided to use definition different tables. So here are examples of TP1 and 2. And so the algorithm is like that. We define physical dimension of properties of good and bad action. Then we code it in Bartini system, and we select factors affecting the conflict, and then logical addition of factor codes, then identify multi-cell and parent trend, and progress along trend. So here is the task of sealing vials, pretty well known task. It should be well sealed, and also the medicine should be good inside. And here flame length should be constant, and melted vial net length should be stable, flame temperature at the vial surface, drug temperature. So we tried 6 factors. And then in couples, we add them logically, we multiply them. And then we got indicator with time, and then we can see trends, you see. Here is trend S plus 1, green one, and red one is S plus 3. And then we look at the proper solutions for us. So according to the trend S3, we are coming to the solution of the spacious volume. We know that here we have geometric volume. X element should be in volume. And we cannot get anything if we consider S plus 3. If we look at the other factors, S plus 2, so the waste of the should be constant in volume. Altshuler said that it should be water, but water is vaporized and it's not considered. And if the spent of this element would be constant, so as much as we lost, we have to add. So that's why table helps us how to do it. So the mass of X element of water should be constant. So this is in brief what I wanted to tell you. So what kind of conclusions do we have here? For example, for teachers, and I'm telling my students how to resolve tests. So the first thing we have to determine how we will measure good and bad action. For example, in Bartini method, we have to know what is good and what is bad, how we seal it well, and how we can measure it. For example, good sealing is the length of the part of this vial. So it should be measured 1 in first degree to the first grade, say first power. So seals well, and so we formulate how. For example, other things are being kind of not in the equation, like repairment, adaptivity, and etc. And also, what kind of conclusions could be made? Of course, it's better to make it with the method of LT dimension search. We can find only the method, not solution. Foreign authors, they try to put it on the matrix of Altshuler and typical methods of technical contradictions. And this very matrix is being drawn to, you see, it doesn't give real answer. It's not written anywhere that it's water. You see, we can find only properties, not one, but several ones. And we have to get a constant expenditure, and but in more wide sense of the word. Yeah, the system Bartini could be used for coding of any properties. For example, what is the difference of speed and power, or power and rigidness, density of current and inertial moment, and etc. That's very important for inventive tasks. And the second thing, that Bartini system suggests some kind of conversion of genes, of length and time, and field resources, the system of field resources. So here genes time, and these are genes in field system. So we cannot find, for example, here is gene of substance field resource, and here you can see literature which was used in the report. So I'm listening to your questions. Thank you very much for your speech, Alexander. Yeah, that's very interesting to hear about specifics in that cluster. And we have one question. For the first time, I can see application of LT systems in trees context. Thank you very much for this interesting direction. Are all physical values could be determined in LT terms as per LT dimensions? Can we measure them for all physical values? Yeah, it's possible. If you know C system dimensions, so dimensionability, so then you can from Bartini system to put it in LT system. For example, mass and let's see, and amount of power, it could be in one cell. So in one cell could be several. So it's because of the worldwide gratitude law. It's you see, it works here. So you can pick whether it's physical value or mechanics. It depends. Worldwide gravity law. So do we use LT dimension anyways? So you see, I have this little textbook. For example, it's like guideline or manual. For example, you have rigidness or viscosity, and you open this value. Yeah, it's clear with mechanical values. Let's work. Let's a charge. Okay, how we can measure it in coulombs? So it's the amount of power of electricity. LT minus 2.
теперь я вам
And
говорю, что я
now
могу другую предложить размерность
I
заряда и,
can
соответственно,
offer
всей
another
электродинамики. Ну, то есть всех величин.
dimensionability
И
of the
точно так
charge.
же будет
Whether
работать.
it work in the same thing
Абсолютно без ошибок. То есть есть
of
неоднозначность.
load.
Вот
So
что я
it's
говорю.
not really clear. You see, there is a system C. In C system, you can use this column as one
Нет, про Си тоже
value.
все понятно.
Yeah, I'm interested in LT
То есть их
dimensionability,
можно
so
вводить
we can
по-разному. Вот что я говорю.
enter them in different ways.
Ну,
I
могу
can
показать,
show you.
могу отдельно
Yeah, we
подискутировать по
can
этому
work.
вопросу.
We can. Yeah, you see, I have a table and I work
Ну,
on
то
it.
есть вы думаете,
So
что
you
заряд всегда
guess
будет
that
один и тот же
the
в
load will be
LT-системе?
the same all the
Нет,
time
это
in
не так.
LT
Есть
system.
два
No,
разных
it's not
способа.
like that. There are
Коллеги,
two
я
different
предлагаю,
methods.
Спасибо.
I can see that there
закрутилась
is
очень
very
интересная
good
интрига, да,
intrigue
дискуссии.
and
Вам
discussion. You see, this matter is known for 1,000 years. They talk a lot about it. There is a person who writes that it's not like that, but okay, thank you very much for this very peculiar, interesting discussion. And I suggest that you would continue afterwards. I won't debate, I won't argue. If the person wants to be in that system, I'm working in Bartini system, that's it.
Коллеги, мы
So,
завершаем
colleagues, we are finishing the work of our session, and I would like to give the floor to Mikhail Semyonovich, and I would like to give thanks to all the speakers and participants who participated in this session, and I'm giving the mic to our host. Colleagues, thank you very much for your participation. Special gratitude to our speakers, interpreters, organizers. As per me, it was rather interesting. And I hope that all the participants got some profit and benefit out of it. So I remind you that tomorrow we start 10 minutes earlier than usual, 10 to 12 Moscow time. So it will be 11:50 a.m. Moscow time. Yeah, we are gathering here in 11:40 and we start at 11:50 a.m. Moscow time. And it's very important for you to answer to the questionnaire questions which will be there after the finish of our conference. Have success, good luck, good mood to you. See you tomorrow. Thank you very much to all of you. Thank you.
Спасибо, до свидания.